Okay, so this is the YouTube video that I'm creating for the physics extra credit assignment for Mr. Wellman's Physics 115 class. So I'm just going to quickly go through the questions and post it as a YouTube video. So the first question here is was about the bubble chamber. So it gave a scenario in which two particles are launched with the same velocity, and the picture shows them going in different directions. So the first question was, what can you conclude about the signs of the two particles if they create circles in the magnetic field at opposite directions? So what I said is that it could be concluded that the particles have opposite signs because they're being repelled in opposite directions. The way I determined this was judging by the equation R equals mv divided by qb, where basically all of the criteria for the particles are the same except for the sign of q, and that would cause the direction of velocity to be opposite, essentially. The second question was asking about the fact that the circles aren't identical, that the path of the particle on the right is larger than the path of the particle on the left. And so I was asking which one had more initial momentum. And I said, once again, according to the equation, particle with largest initial v, assuming that they had equal mass, will have the larger radius of trajectory. So this is the particle on the left. Then finally, for this question, the path spiral inwards. So it's asking why did the path spiral inward? And I said that this is because the magnetic field must be in a gradient, and so an increasing B, according to the equation, would cause the R to decrease over time. So kind of through the space that they're traveling, you have an inconsistent B value. Yeah. So the next question we have here is asking about, it says a charged particle is fired into a cubical region of space where there's a uniform magnetic field. It's asking, is it possible that the particle will remain inside the cubical region? Well, I said that it really depends on the scenario. And so once again, we're going back to our Lorentz equation where R equals mv over qb. So if the relationship between mv over mv and qb, if that R that is yielded is greater than the bounds of the box, then the particle will leave the box. I think I wrote that wrong. But yeah, so if R is greater than the bounds of the box, then the particle will leave the box. However, if the bounds are less, or if the R is less than the bounds of the box, then the particle will remain in the box. I'll change it on my hard copy. The third question, talking about a particle once again. So this says that a charged particle moves through a region of space with a constant velocity, magnitude, and direction. If the external magnetic field is zero in this region, you can conclude that the electric field in the region is also zero. And I said, yes, the electric field is zero. According to the equation, F equals, so force equals charge times the electric field. If there is no E, then there is no force, which would mean that the change in velocity there'd be no change in velocity. So we're seeing that there's no change in velocity, and so the E must be zero. Because if there was any sort of force, then the particle would be changing speed, either accelerating or decelerating. However, this is not the case for a magnetic field. In a magnetic field, you can have a B that exists, and then it'll maintain the same velocity. And you'll see this in that the particle will oftentimes will go in like a circular path and not really deviate from that path as long as everything else remains constant. Next question here, this is a mass spec question. So this is asking between three different isotopes of carbon, between three different isotopes of carbon, what will the radius of their trajectory be through the mass spectrometer? And so this one was pretty just kind of like plugging and chugging. First, I found the mass of each particle. First I found the mass of each particle of each isotope, and then I threw that mass into into the mass spec equation with the information that was given. So I'm just going to go over one. So for the carbon-12, which is the most common isotope of carbon, we have the mass times its initial velocity, which is the same throughout. Then you have the magnetic field, which is 0.68 Tesla. And then you have the charge of that particle, which is 1.6 times 10 to the negative 19 coulombs. So each of them has a single charge as well. And so we find that as the mass increases, the radius of the particle increases in the mass spectrometer. And so really the question was asking what is the differences between the radii. And so once I found the radiuses, I just subtracted them from each other. So the difference between carbon-12 and carbon-13 is 7 times 10 to the negative 4th meters. That's the radius. And the difference in the radius between carbon-13 and carbon-14 is 3 times 10 to the negative 4th meters. Then the next question was asking if the ions were doubly charged, well, how would the radius change? And so I said that according to the equation, if the ions were doubly charged, since that charge value is in the denominator, if it was doubled, then the radius would be cut in half. And then this would subsequently reduce the distance between them in half as well. Next question. We have, this is in which a charged particle is moving in a circle under the influence of a uniform magnetic field. If an electric field that points in the same direction as a magnetic field is turned on, describe the path the charged particle will take. And so this one, kind of what I was describing earlier, is that if a particle is moving in a circle in a magnetic field, it'll kind of maintain that circle. But if you introduce an electric field to it, it's going to create a force, and so it's going to cause the velocity of the particle to change, and subsequently its position in space. So it'll cause it to take on a corkscrew sort of pathway through space. Then number 6, we have the scenario is that we have a doubly charged helium atom whose mass is 6.6 times 10 to the negative 27 kilograms, and it's accelerated by a voltage of 2100 volts. And so what is the radius of the curvature if it moves in a plane perpendicular to a uniform 0.340 Tesla field, and what is the period revolution? And so you see my work here. So for the first problem, we're asking for the radius, and so I solved this. There is some algebraic manipulation here, and so I took my force equation, solved it for mv, and then I took the force equation, solved it for mv, and then I plugged it into the inertia equation, which is the 1/2 mv squared. Then through some algebraic manipulation, I came to the conclusion that R equals the square root of 2 mv over qb squared. And so plugging in the values that were given, I found that the radius of the particle is 2.74 times 10 to the negative 2 meters. And then the period per revolution, so so I know that the period is 2 pi r divided by v, and so that's distance over speed, and doing some algebraic manipulation as well, plugging in what I know that v is simplified, and I found that the period is per single revolution is 3.81 times 10 to the negative 7th seconds for this particle. For question 7, it just asks to draw with appropriate arrows the direction that the magnetic field is pointing from each of these points. And so we have a long straight wire which carries a current I out of the page at this I value here. And so it's asking what is the direction of the magnetic force coming off of I at these subsequent points. And C is very self-explanatory, since C is right above it according to the right-hand rule. All these according to the right-hand rule. The magnetic field for C is going to be to the right. The magnetic field for D is going to be at kind of a 45-degree angle. The magnetic field for E is going to be directly down. Finally, last question is asking about A circular coil with a 16 centimeter in diameter containing 9 loops lies flat on the ground. And so we're wondering, based on the Earth's magnetic field um, and the angle of the Earth, what is the torque on the coil based on the magnetic field of the Earth? And so you see my equation. I'm just using the torque equation. So we have torque equals n number of loops times the current times the magnetic field times the area of my coil times the cosine of the angle between the Earth and the coil, which is 56 degrees. So plugging all those in, the torque is 3.98 times 10 to the negative fifth Newton meters. And I can also turn from this as asking what direction will the loop turn, and so I said due to the fact that the normal moves towards the magnetic field, and the north edge of the coil will rise up. So that concludes all the questions for the extra credit assignment. Thank you.